Today, I'll present results from our research titled CT-based dosimetry in Y-90 Radioembolization performed in a rabbit liver model. Here are our disclosures. To begin, radioembolization is a well-established treatment for inoperable liver cancer where radioactive microspheres are administered into the hepatic arterial blood supply to embolize the tumor's microvasculature and deliver tumoricidal doses of radiation. Glass microspheres are infused with Y-90, which decays through the emission of high-energy electrons and less often high-energy positrons. Between the Bremsstrahlung and coincident photons produced in this decay, we can perform both SPECT and PET imaging to provide estimates of the absorbed dose in radioembolization. The issue with SPECT and PET imaging lies in their poor spatial resolution. Reconstructed voxel sizes are orders of magnitude larger than the distance scales over which changes in microsphere concentration takes place, as demonstrated in these microscopy images of microsphere distributions in ex vivo liver tissue samples. And as a result, PET and SPECT imaging prevent accurate quantification of the true dose heterogeneity, which is an important thing to understand because low dose regions in these tumor volumes are correlated with the chance of local recurrence. Here's a recent review article summarizing dose response studies in radioembolization titled "To 1,000 Gray and Back Again." As the authors found, the mean dose required to observe a tumor response was found to range a full order of magnitude. So it's essential to accurately define this threshold because this is the minimum dose we aim to deliver to effectively treat the tumor. Now, if more accurate estimates of the microsphere distribution can be obtained with higher resolution imaging, it would improve our estimates of the absorbed dose and hence our understanding of that dose-response relationship. So we have an unmet clinical need to provide higher spatial resolution imaging to facilitate high accuracy dosimetry in radioembolization. We can look to CT for that improvement in spatial resolution. A radiopaque microsphere has been recently developed by ABK Biomedical with its inherent radiopacity, a consequence of the high Z compounds within the microsphere's composition. So when we increase that effective atomic number of the microsphere, we increase the probability of it fully absorbing an incident X-ray, which is responsible for providing the excellent image contrast shown in these micro CT images of an embolized pig kidney. So the hypothesis of our work is that CT imaging of these radiopaque microspheres can drastically improve our dose estimates in radioembolization. So the study goals to first investigate the relationship between microsphere concentration and CT Hounsfield units. Then to perform, based on those results, perform CT-based dosimetry in a rabbit liver model. And then to compare those extracted dose metrics to those produced from PET-based dosimetry. To investigate the relationship between microsphere concentration and Hounsfield units, we designed a calibration phantom containing posts of various microsphere concentrations. In the central image here is an axial CT slice of the phantom overlaid with structures specific to the microsphere concentrations in the posts, with the blue structures for the 25 milligram per milliliter posts, red for 5 milligrams per mil, and green for 0.5, and the magenta for the background region void of microspheres. So a CT calibration curve was then determined by measuring the average Hounsfield unit and the largest posts for each microsphere concentration, and then plotting those averages against the nominal concentration within those regions. So this curve allows us to transform any CT Hounsfield unit into a radiopaque microsphere concentration. Once we've established that calibration curve, we begin PET-CT imaging of the rabbit cohort. Approximately 40 milligrams of microspheres were administered into the livers of 8 individual rabbits, followed by a PET-CT acquisition, which provided us with a PET-based activity distribution represented by the orange overlay in this fusion image. And we used the results of that calibration curve, apply that to the radiopaque regions within this CT, and that allows us to produce a CT-based activity distribution. And equipped with these two Y-90 activity distributions, we can then use a voxel-based dosimetry formalism to calculate the absorbed dose. So how exactly do we do that? How do we calculate the absorbed dose given a CT-based activity distribution? After we apply that calibration curve to translate a voxel's Hounsfield unit into a microsphere concentration, we can calculate the activity by multiplying that concentration by 3 factors: the voxel volume, the number of microspheres per milligram, and the microsphere's specific activity. And then to calculate the dose, we perform a mathematical operation defined in the next slide. So this operation is called convolution. The dose to a voxel is equal to the convolution of what's called a dose voxel kernel and the accumulated activity distribution, where this kernel defines the spatial distribution of the emitted Y-90 energy. To generate these kernels, we performed Y-90 radiation transport simulations in a spherical water phantom and tracked the deposited energy in each voxel within the phantom. This simulation was run for voxel sizes specific to both CT and PET image volumes. And to demonstrate this equation pictorially, on the top row, we have a 2D cross-section of the CT kernel and an axial slice of that CT accumulated activity distribution, with the corresponding PET images shown in the bottom row. Note the kernel shape here, how the shape changes and the magnitude of the central voxel differs as a result of the different PET CT voxel sizes, but both kernels contain the same amount of deposited Y-90 energy within that spherical phantom. Okay, here we have an example of a CT and PET-based dose distribution on the top and bottom rows respectively, with axial, sagittal, and coronal slices in each of the three columns. The CT-based dose distribution contains very steep dose gradients and is highly correlated with the radioembolized vasculature as it was derived from the microsphere distribution itself. Now, the PET-based dose distribution, it predicts low dose to regions that are clearly void of radiopaque microspheres. Furthermore, the dose is significantly more homogeneous, and a larger fraction of that dose lies outside of the contoured liver, likely a result of respiratory motion, which is almost entirely mitigated in CT. At the location of the crosshair in the image, CT-based dose value is over 1600 gray, while the corresponding PET dose is only 230. In the table below, we report several dose metrics, the maximum, mean, and standard deviation of the dose values within the contoured liver. Note the exceedingly high dose, over 1800 gray in the CT-based dose distribution, and the larger standard deviation both indicate that the CT dose contains a much wider range of dose values within the liver relative to PET. Still, the mean absorbed dose to the liver only differs by 20 gray in this case, which is expected as the liver contains the same amount of Y-90 activity in both cases. So to conclude, we've demonstrated a strong positive correlation between radiopaque microsphere concentration and CT Hounsfield units. And despite attributing a similar mean dose, CT dosimetry depicts that dose heterogeneity with increased accuracy relative to PET. And this CT-based approach can provide clinicians with an opportunity to further develop their understanding of that dose-response relationship in order to ultimately improve future patient outcomes. And in future work, we aim to validate this CT-based approach in a hypervascular tumor model. I'd like to thank all the co-authors who participated in this study, our funding agencies and collaborators, and thank you all for listening. I'd be happy to take any questions. Thank you.
Yeah, thanks a lot for that extraordinarily detailed presentation. I mean, there's some math on there that I don't even remember from my medical school and undergraduate days. I mean, it's kind of complex. I give you guys a lot of credit to get through all that.
Yes,
does anybody, you're welcome. Does anybody have any specific questions on the panel?
I'm just going to ask quickly this question. What's the size of the this actually radiopaque beads? Do you guys see any embolic effect from it? Like, I mean, is it similar mostly? Is it similar to, I would say, like resin or like glass base?
They are very similar in size and in density to thermosphere glass microspheres. So there's no embolic effect observed that you would see relative to the resin-based microsphere.
And radioopacity is coming from. So do you guys have iodine on board? Is that like how you guys measuring it?
So it's the radioopacity is a consequence of all of the high Z compounds that constitute the microsphere composition itself. So it's a glass microsphere, but we incorporate those high Z compounds to further increase that radioopacity.
Thank you.
Did you correlate with ex vivo sort of necroscopy samples of the rabbits to see in areas where PET and CT sort of differed in dose, what those areas look like in the liver?
Unfortunately, no, we didn't have the opportunity to do that yet. In a previous study that we did, we actually, the embolized pig kidney I showed, we actually had an opportunity to do some cross-sectional studies on that. So we have the data potentially to compare a micro distribution to a macro distribution, but we haven't yet done that study. That would be interesting to do in order to sort of see where those differences lie within PET and CT, as you mentioned. That would be a good study. Yeah.
Really interesting study. I wonder, do you guys think that you're perhaps going to underestimate the dose to normal liver in a real model because of the relatively few microspheres there? Your Hounsfield unit may not be as accurate as compared to a densely packed area.
Yeah, so that's a very good question. We can see from those images, there are sort of macro vessels that are embolized, and then sort of a blush region embolized to a much lesser extent, as indicated by those Hounsfield units. So we've developed the slope, that calibration curve, based on the data from the largest posts within the calibration phantom. But if we calculate those slopes based on the smaller diameters, we see slight changes in that slope, which indicates that perhaps we may need to apply those separately. So maybe separate the liver into macro and micro embolization and apply 2 different slopes to those regions in order to be sure that we're accurately determining that dose, I suppose. So it can be a complex issue if you're simply using one calibration curve, but we're going to look into potentially exploring multiple regions and multiple calibration curves to fully make sure we're quantifying that activity appropriately.
Great, thank you. I think we'll, unless there's other questions, we'll move on to the next